We will keep talking about rearrangements of the ideal gas law. We have talked about partial pressure, etc., how we can use the ideal gas law in different ways. In this case, we will try to use the ideal gas law to talk about concentration and density. Most of you may not know, it depends if you heard it before. Concentration by definition is number of moles over unit of volume, typically liter. And density, you may be more familiar, it's grams or mass in general, typically it's grams in chemistry, over volume, over unit of volume, typically liter. Okay, let's first talk about how we can talk about concentration in ideal gas law. Notice that we can arrange the ideal gas law by moving the V to the other side in the denominator, and notice here that by definition the moles over volume is what we call concentration. So concentration will be directly proportional to the pressure. If concentration increases of a gas, keeping temperature constant, the pressure will increase. So let's solve a problem, a simple problem. In this case, we are reading from here. A sample of hydrogen and a sample of oxygen are in two different containers, and it says that both are at the same temperature and pressure. And the question is, do they have the same concentration? Well, you just need to look at this, and we can, if you want, we can put concentration on one side and pressure and temperature on the other. You can see now that if pressure and temperature are constant, it means that the concentration, the moles over volume, will be constant. So concentration in this case is the same because pressure and temperature is also determined. We can have a similar discussion in this case about density. Density, however, is not number of moles, so we need to use the ideal gas law and transform the number of moles here into grams. Okay, so notice that how can you calculate the grams? Well, typically the grams you can calculate it by multiplying number of moles times molecular weight, or in other words, so the number of moles is grams over molecular weight, right? So you put this into the ideal gas law, and what you see is this, where this probably it's an unfortunate, it's supposed to be the rho, the RHO, the Greek letter rho. It's the symbol for density. If you prefer, you may want to use the term D, where density divided by the molecular weight of the gas, RT. All right. So here you have the ideal gas law expressed in terms of density, that is, mass over volume. So let's solve a problem. A sample of hydrogen and a sample of oxygen, we are in the same place here as before. They have the same temperature and pressure. They are the same. The question is, do they have the same density? Well, in this case, the density, I'm just rearranging it from here, will be pressure times molecular weight divided by RT. Notice that pressure and temperature are the same, but molecular weight is not. Okay, molecular weight is higher in oxygen, so it will have, the container with oxygen will have a higher density, and the container with hydrogen will have a lower density because you will be multiplying by either a larger or a lower molecular mass. Hopefully that makes some sense. Let's solve another problem. In this case, we have four containers. Let's draw them. Four containers. One is made out of helium. The other one, it's not made out of helium, contains helium. The other one chlorine. The other one methane. The other one ammonia. They are all at 0 Celsius, which is 273 Kelvin, at 1 atmosphere. Okay, and they all have the same mass. So same mass. Okay, so it asks do they all have the same volume? Okay, well, this is a little bit trickier. You may want to go back here and remember the equations, the P equals CRT. P equals CRT for concentration, and in here the P dRT over molecular mass. P equals dRT. I say molecular mass, molecular weight. Actually, molecular mass is more precise because we're measuring grams per mole, but you know, it's exchangeable. All right, so what we know is that if it has the same temperature and same pressure, they will have the same concentration. The same concentration, both of them. But does it mean they have the same volume? Well, they all have the same mass. All right, so notice that 10 grams, 10 grams, 10 grams, 10 grams, for example, I just made it up, right? Do they have the same moles in here? No. In which case do we have the largest amount of moles? Well, let's see. The lightest is helium, right? Because the atomic mass is 4 grams per mole. We will have more moles. And the heaviest is Cl2 because, let me see, it should be 37, if I'm not mistaken, 72 grams per mole. It's the heaviest, you'll have less moles. So how can it be that if we have more moles in one case, we have less moles in the other case, and yet we have the same concentration? That can only be because we change the volume. So the container with more moles will have to have more volume so that the concentration is the same, right? The container with more moles will have to have more volume so that the concentration is the same. The container with less moles will be the container with the lowest volume so that the ratio is the same, so that concentration is the same. All right, so do they all have the same volume? No. Which one has the largest volume? The one that contains the largest number of moles, because the concentration has to be the same. So when you divide a larger number of moles, you need to divide it by a larger volume so that concentration is the same.